Recently, very important news were published about space generators and a lot of news. The first news with us says, radioisotope thermoradiative cell power generator. In this project we will continue our Phase 1 efforts to develop and demonstrate the feasibility of a revolutionary power source for missions to the outer planets utilizing a new paradigm in thermal power conversion, the thermoradiative cell or TRC. Operating like a solar cell in reverse, the TRC converts heat from a radioisotope source into infrared light which is sent off into the cold universe. In this process, electricity is generated. In our Phase 1 study, we showed 8 watt of electrical power is possible from the 62.5 watt Pu-238 pellet from a general-purpose heat source using a 0.28 eV bandgap TRC operating at 600 Kelvin. The necessary array includes 1,125 square centimeters of TRC emitters, or just over 50% of the surface area of a 6U CubeSat. With a mass of 622 grams, a mass-specific power of 12.7 W/kg is possible, over a 4.5x improvement from Heritage Multi-Mission Radioisotope Thermoelectric Generator or MMRTG was shown. Building on our results from Phase 1, we believe there is much more potential to unlock here. Using low bandgap materials such as INASSB and nanostructured arrays to limit potential loss mechanisms, a 25x improvement in mass-specific power and a 4 order of magnitude decrease in volume from a MMRTG is an early estimate, with higher performance possible depending on operating conditions. TRC technology will allow a proliferation of small versatile spacecraft with power requirements not met by photovoltaic arrays or bulky, inefficient MMRTG systems. This will directly enable small SAT missions to the outer planets as well as operations in permanent shadow such as polar lunar craters. This study will investigate the thermodynamics and feasibility of the development of a radioisotope-enabled thermoradiative power source focusing on system size, weight, power while continuing to integrate the effects of potential power and efficiency loss mechanisms developed in Phase 1. Experimentally, materials and TRC devices will be grown including superlattices by metal organic vapor phase epitaxy to target low bandgap materials with suppressed Auger recombination. Metal semiconductor contacts capable of surviving the required elevated temperatures will be investigated. TRC devices will be tested for performance at elevated temperature facing a cold ambient under vacuum and a modified cryostat testing apparatus developed in Phase 1. We will analyze a radioisotope thermoradiative converter to power a CubeSat mission operating at Uranus. This will include an engineering design study of our reference mission with the Compass engineering team at NASA Glenn Research Center with expertise on the impact of new technologies on spacecraft design in the context of an overall mission, incorporating all engineering disciplines and combining them at a system level. Finally, we will develop a technological roadmap for the necessary components of the TRC to power a future mission. The second news with us says, NASA selects BAE Systems to develop air quality instrument for NOAA. NASA, on behalf of the National Oceanic and Atmospheric Administration, has selected BAE Systems of Boulder, Colorado, to develop an instrument to monitor air quality and provide information about the impact of air pollutants on Earth for NOAA's Geostationary Extended Observations Satellite Program. This cost-plus award fee contract is valued at approximately $365 million. It includes the development of one flight instrument as well as options for additional units. The anticipated period of performance for this contract includes support for 10 years of on-orbit operations and 5 years of on-orbit storage, for a total of 15 years for each flight model. The work will take place at BAE Systems, NASA's Goddard Space Flight Center in Greenbelt, Maryland, and the agency's Kennedy Space Center in Florida. The GeoXO atmospheric composition instrument is a hyperspectral spectrometer that measures a wide spectrum of light from ultraviolet to visible. The instrument will provide hourly observations of air pollutants emitted by transportation, power generation, industry, oil and gas extraction, volcanoes, and wildfires as well as secondary pollutants generated from these emissions once they are in the atmosphere. By providing continuous observations and measurements of atmospheric composition, ACX data will improve air quality forecasting and monitoring and mitigate health impacts from severe pollution and smoke events, such as asthma, cardiovascular disease, and neurological disorders. Data from ACX also will help scientists better understand linkages between weather, air quality, and climate. The contract scope includes the tasks and deliverables necessary to design, analyze, develop, fabricate, integrate, test, verify, evaluate, support launch, supply and maintain the instrument ground support equipment, and support mission operations at the NOAA Satellite Operations Facility in Suitland, Maryland. The GeoXO program is the follow-on to the Geostationary Operational Environmental Satellites. The GeoXO satellite system will advance Earth observations from geostationary orbit. The mission will supply vital information to address major environmental challenges of the future in support of weather, ocean, and climate operations in the United States. Advanced capabilities from GeoXO will help address our changing planet and the evolving needs of NOAA's data users. NOAA and NASA are working to ensure these critical observations are in place by the early 2030s when the GOES series nears the end of its operational lifetime. Together, NOAA and NASA will oversee the development, launch, testing, and operation of all the satellites in the GeoXO program. NOAA funds and manages the program, operations, and data products. On behalf of NOAA, NASA, and commercial partners develop and build the instruments and spacecraft and launch the satellites. The next news with us says, Sciencecraft for outer planet exploration. Missions to the outer solar system are an important part of NASA's goals because these scarcely visited worlds, particularly the ice giants Neptune and Uranus, hold secrets about the formation and evolution of our solar system and countless others. However, due to the high cost, long travel time and narrow window for mission implementation, outer solar system exploration has been extremely limited in more than 60 years of space exploration. In this NASE, we are developing a mission architecture that addresses all of these challenges by using a sciencecraft and enables science missions at the outer planet system. Sciencraft integrates a science instrument and spacecraft into one monolithic and lightweight structure by printing an ultra-lightweight quantum dot-based spectrometer, developed by the PI Sultana. Directly on the solar sail, we create a breakthrough spacecraft architecture allowing an unprecedented parallelism and throughput of data collection and rapid travel across the solar system. Unlike conventional solar sails that serve only to propel small CubeSats, Sciencraft puts its area at use for spectroscopy, pushing the boundary of scientific exploration of the outer solar system. Sciencraft offers an attractive low-resource platform that can enable science missions at a significantly lower cost and provide a large number of launch opportunities as a secondary payload. By leveraging these benefits, we propose a mission concept to Triton, a unique planetary body in our solar system, within the short window that closes around 2045 to answer compelling science questions about Triton's atmosphere, ionosphere, plumes and internal structure. In Phase 1, we performed an end-to-end feasibility study for a Neptune-Triton mission using a sciencecraft. As well as identifying the key technologies needed for such a mission and tall poles that we need to address, as part of Phase 2, we plan to further mature the mission concept, develop and demonstrate some of the key technologies, address the tall poles identified in Phase I and develop a roadmap for implementing scope. The last news with us says, the Great Observatory for Long Wavelengths. Humankind has never before seen the low-frequency radio sky. It is hidden from ground-based telescopes by the Earth's ionosphere and challenging to access from space with traditional missions because the long wavelengths involved require infeasibly massive telescopes to see clearly. Electromagnetic radiation at these low frequencies carries crucial information about exoplanetary and stellar magnetic fields, the interstellar/intergalactic medium, and the earliest. The Great Observatory for Long Wavelengths proposes an interferometric array of thousands of identical smallsats at an Earth-Sun Lagrange point to measure the magnetic fields of terrestrial exoplanets via detections of their radio emissions at frequencies between 100 kHz and 15 MHz. Each spacecraft will carry an innovative vector sensor antenna, which will enable the first survey of exoplanetary magnetic fields within 5 parsecs. In a departure from the traditional approach of a single large and expensive spacecraft with many single points of failure, we propose an interferometric Great Observatory comprised of thousands of small, cheap, and easily replaceable nodes. Interferometry, a technique that combines signals from many spatially separated receivers to form a large virtual telescope, is ideally suited to long-wavelength astronomy. The individual antenna/receiver systems are simple, no large structures are required, and the very large spacing between nodes provides high spatial resolution. The Phase 1 study showed that the key innovation for Go Low is the system of systems. The technology needed for each individual piece of the observatory is not a big leap from current state-of-the-art, but the coordination of all these physical elements, data products, and communications systems is novel and challenging, especially at scale. In the proposed study, they will develop a real-time, multi-agent simulation of the Go Low constellation that demonstrates the autonomous operations architecture required to achieve a large constellation outside of Earth's orbit. Continue to refine the science case and requirements by simulating science output from the constellation and assessing major error sources informed by the real-time simulation. develop appropriate orbital modeling to assess propulsion requirements for station keeping at a stable Lagrange point, and further refine the technology roadmap required to make Go Low feasible in the next 10 years. Go Low represents a disruptive new paradigm for space missions. It achieves reliability through massive redundancy rather than extensive testing. It can evolve and grow with new technology rather than being bound to a fixed point in hardware/software development. Finally, it promises to open a new spectral window on the universe where unforeseen discoveries surely await. Thank you very much for watching. Goodbye.